suppose I'm audible and my screen is clearly visible. Is that okay?
Yes, sir.
Perfect, perfect. Right. So, this class is about fluorescence spillover and compensation, as I said. A very, very important topic. Normally, we use this term commonly, compensation in flow cytometry language. What exactly this means is what we are going to see about in this class. Right. Now, we just saw this in the third lecture, that is in fluorescence and fluorochromes. So this is called spectral overlap. What is spectral overlap is, you have two fluorochromes. Remember, don't confuse it with Stokes shift, okay? Stokes shift is something which comes into play when you are discussing about a single fluorochrome. Okay, now this is spectral overlap, where this comes into discussion when you are working with multiple fluorochromes, more than one fluorochromes. Okay, now for example, this is fluorochrome A, and this is the emission spectrum of that particular fluorochrome. Okay, you know what is excitation spectrum, what is excitation maximum, you know what is emission spectrum and emission maximum, correct? Now, this is the emission spectrum of fluorochrome A, and this is emission spectrum of fluorochrome B. The emission maximum of fluorochrome A lies somewhere here, okay, and similarly the emission maximum of fluorochrome B lies somewhere here, okay. Now, if you closely look, a part of these two overlap. The spectrum of fluorochrome A and fluorochrome B overlap in one particular area. This overlap of emission spectrum between two fluorochromes is called spectral overlap. Clear? Right. Now, this we see it with a particular example with respect to two very commonly used fluorochromes, which is FCM and PE. Okay. Now, similarly, FCM emission spectrum is somewhere around 490 to 610, something like that. And similarly, the emission spectrum of PE is somewhere between 550 to say 700. Okay. Now, if you, and the emission maximum of FCM is somewhere around 550, and the emission maximum of PE is somewhere around 590. Okay. Now, if you see these two fluorochromes emission spectrum, there is an area again where there is an overlap. This is called spectral overlap. Okay. Now, what is the problem with the spectral overlap? Anyone who wants to take a think? What is the problem with this overlap? Okay, I'll tell you. Now, this is another example. Okay, the same image. So I'm again discussing about FCM or Alexa Fluor 488. Both are very similar fluorochromes with respect to excitation and emission. And the other fluorochrome is PE. Okay. Now both these fluorochromes are excited by blue laser, which emits light at 488 nanometer. Blue light at 488 nanometer. Okay. Now, once both Alexa Fluor 488 and PE get excited, they give emission spectrum. Okay. Now, this emission spectrum, as we saw, is a range of wavelength, and similarly, the emission spectrum of PE is also a range of wavelength. And as we discussed, there is a overlap between the emission spectrum of both the fluorochromes. Now, what is the problem here is, now I have a flow cytometer and I have a detector to pick up the signals from Alexa Fluor 488 in FL1 channel. Okay. Now, this detector will have a band pass filter. You know what is band pass filter? We discussed in lecture 2, right? So, it will allow only light of one specific wavelength. Now, I suppose this is a band pass filter which is 525. Okay, so this is band pass filter which will allow light between 525 plus or minus 15. Okay, so it allows light between 510 to 540. Similarly, to take the PE light, again the PE detector, which is FL2 detector. Okay, it has a band pass filter between 575 band pass filter. Okay, so it plus or minus 25 minutes, it will be around 550 to 600. Okay, so every specific fluorochrome will have a specific detector which will with an optics of band pass filter which will filter the light before hitting the detector. Okay, now if you find this spectral overlap will cause a problem here. If you see the emission spectrum of Alexa Fluor 488 or FITC, you see that some part of this emission light, FITC emission or Alexa Fluor 488 emission light is going through the bandpass filter of PE channel. So because of this, what happens in the PE, you will get a FITC signal, which should not happen, because the PE detector or the PE channel should collect light only from fluorescence of PE. Correct? And similarly, Alexa Fluor 488 channel or Alexa Fluor 488 detector should capture signal only from this particular fluorochrome. Okay, but since there is a spectral overlap, as we saw between these two fluorochromes, a part or a small fluorescence from Alexa Fluor 488 will spill over into the PE detector or PE channel. This is called spillover. Okay, and the process to eliminate this or minimizing this or subtracting it or avoiding it is called compensation. Okay, so we'll just see this in more detail. So again, this is emission spectra of FITC. So the one in the dotted is the excitation spectrum, and this is the excitation maximum. So normally we excite FITC and PE both with blue laser, which gives light at 488 nanometer. So once it goes for excitation, the emission spectrum is from, as I said, 490 to 650 nanometer for FITC, whereas the emission emission maximum is around, say, 520 or 530. Okay, and you have a specific detector with a bandpass filter 530 plus or minus 30. So this FL1 channel or FITC detector will collect light of wavelength 500 to 560. It will not collect it will not detect light less than 500, or it will not detect light greater than 560. Okay, similarly we have another detector which is particularly to collect only light from PE channel or PE fluorochrome. Okay, and similarly we have a FITC detector which is very strictly should collect only light from FITC fluorochrome. Okay, but since the emission spectra of FITC is so broad, okay, some amount of this light which is from nanometer, because the fluorescence when it is emitted from a fluorochrome, it is not a monochromatic as your laser light. Okay, that's why we saw whenever a fluorochrome is emitting light, it is a spectrum. Similarly, excitation also can happen to a range of wavelength. It is not like only in one particular wavelength it will get excited. It will, at one particular wavelength, it will get excited to the maximum, that is called excitation maximum. Okay. Similarly, in emission, it's a spectrum, but the maximum emission is happening at 530, for which you have, that is the reason why you have kept a filter like this to collect the FITC light or the FL1 channel fluorochrome light. Okay, but since the emission spectrum is so broad, okay, some amount of this light from, say, for example, 575 to 600, okay, this FITC light can be detected by the PE detector, because PE detector has a bandpass filter 585 plus or minus 42. So anything between 540 to 620, this PE detector will take up. So some part of fluorescence emitted from the FITC fluorochrome can get collected in the PE detector, which should not happen. Okay, and this spillover of FITC light into the PE channel or the FL2 channel is called spillover, and the process of correcting this is called compensation. Okay, so is that clear? Okay, so every fluorescent molecule can emit light with a spectrum characteristic of that molecule. Okay, again, it's a spectrum. Okay, range of wavelength. However, the emission spectrum of two molecules can overlap, as we just saw with FITC and PE. Okay, for example, FITC and PE. Okay, this is called spectral overlap. Some of the FITC fluorescence can appear in the detector designated for PE. So PE detector is designated to collect light only from PE fluorochrome. Okay, but since the emission spectra of the other fluorochrome, which is FITC, is very broad, some amount of FITC light can get collected in the PE, and that is called fluorescence spillover. Okay, so I am telling you with example with FITC and PE, but it can happen across any number of fluorochromes. Okay, FITC light can go into PE, it can also go into FL3 channel to a bit. Okay, similarly, this spectral overlap between tandem dyes would be more. Okay, and spillover between tandem dyes will also be more because of that. Okay, so this is called fluorescence spillover, and the process of correcting this is called compensation. Okay, is that clear now? Any doubts? If you have doubts, please put in the chat box. Okay, I'll take up the question. Is that clear? Fluorescence spillover, right? If you have any doubts, please put it in the chat box. I'll take the questions. Yes. Yeah, clear. Perfect. So we'll go ahead. Slowly we'll go because this is very important topic. So I don't want to go in a hurry. Okay. Now, how do you check whether spillover is happening? For example, now you want to check whether your FITC fluorescent from your FITC fluorochrome is getting spilled over into other channels. Okay. Normally FITC signal will be collected by FL1 channel, that is fluorochrome 1 channel. Normally we just call that like, or to avoid confusion, I'll say it's a FITC fluorochrome should be collected only by FITC channel. It should not be collected by any other channels like PE channel, ECD channel, PC5 channel, PC7 channel. So the other channel should not collect FITC channel. So FITC light should be collected only by the FITC channel. But how to check whether this spillover is happening or not? What will you do? Any random guesses? Any random guesses? How do you want to check whether the fluorochrome designated, the channel designated for that particular fluorochrome only is collected light, and the other channels are not getting light from the emitted fluorescence of one particular channel, say for example FITC. Okay, so how do we do this is, I'll tell you. Now I will take a sample and stain only with FITC. Okay, so I may be using a 10 color instrument. Okay, now what I'm going to do, I'll take a sample and I label only it with FITC fluorochrome. Okay, then I run the sample in the flow cytometer. Then I'll check in the FITC channel. Okay, in FITC channels there is a signal. Correct? There is a signal. But if you find in the PE channel also there is a signal. Is this correct? Is this correct? It should not come, right? So because I have stained the cells only with FITC, then how come a signal can come in PE? This is wrong. So this is something wrong. So there is a FITC fluorescence is getting spilled over into PE. Okay. So this is how we need to check whether spillover is happening. So basically this is called, we'll stain the cells with only one particular fluorochrome and observe for signal in all the fluorochromes. Ideally, you should get signal only in the fluorochrome which you have stained. For example, only FITC channel should show signal if you have stained the cells with only FITC. Okay, if you get signal in PE, ECD or other channels, it means the FITC fluorescence is getting spilled over into the other channels and you need to correct it. So that's how you check the spillover is happening or not. Okay, so this is correct. Okay, since I have stained the sample only with FITC, this is correct. But PE signal is also coming. So this is negative. This is a small peak of positive signal is coming. So this is because of compensation. This is histogram. Okay, and this is a dot plot, which is again showing that there is some amount of FITC spilling over into PE, going into PE. Okay, and this is because of this particular thing. The emission spectrum of FITC is so broad that a part of FITC light is within the bandpass filter of PE channel and it is getting into that and giving a signal in the PE channel. Okay, clear? So this is how you check whether spillover is happening or not. Okay, now what is compensation? Compensation refers to correcting a phenomenon called fluorescence spillover in flow cytometric analysis. Okay, so I repeat, compensation refers to correcting a phenomenon called fluorescence spillover in flow cytometric analysis. This is removal of signal of any given fluorochrome from all the detectors except the one dedicated to measure a specific fluorochrome. As I said you, so if I'm using FITC fluorochrome, okay, and I'm running the sample, I should remove all the signals in the all other detectors except FITC channel. Okay, and that process is called compensation. Okay, so compensation is very important, and sometimes it's not understood, and we just ignore it, which can lead to very bad results. Okay, and even wrong diagnosis. Okay, so again, this is another example I just want to show you. So this is again a 488 laser, and this is your FITC. Okay, now if you see the emission spectrum of FITC, it is the emission maximum of FITC is correctly within the FTC channel filter, FTC detector. Okay, so this is a bandpass filter. Okay, and if you see, a part of this emitted FTC light is also getting collected in the next channel, which is the PE channel. And if you see, there is a part of emitted FTC light which also comes within the range of third channel, which is the ECD channel or PE sci-fi channel. Okay, so you find the FTC signal is spilling over into PE, it is also spilling over into PC5. Okay, so this one you need to understand. Okay, so this is spectral spillover. Again, I'm repeatedly showing you because I want you to understand this. Okay, now FTC, again the emission spectrum of FTC is broad. Okay, so this is the FTC channel with the bandpass filter of 530 plus or minus 30. So it is collecting maximum FTC light. And this is the next channel, which is PE channel with the bandpass filter of 575 plus or minus 26. If you see, a part of FTC light, okay, a part of FTC light is within the wavelength of this particular filter. That is between 550 to 600. And hence, a part of FTC light will also get collected in the PE detector. And it will give you signal in the PE channel. Okay, which is wrong. Okay, and you need to eliminate this. This process of eliminating this non-specific signal into the PE channel from FTC is called compensation. Okay. So see, this is the spillover. So out of 100% FTC, 22.7% of FTC light is getting collected in the PE channel. And similarly, if you closely observe, out of 100% of the PE fluorescence, emitted fluorescence, 0.7% is getting collected in the FTC channel. Okay, now what I need to do is, out of this 100%, I need to subtract this 22.7% from the FTC channel. And similarly, from the PE signal, I need to subtract this 0.7% to get correct signals in respective channels. Okay, so this is how I do this. So out of, as I discussed, so this is FTC. If you see in FTC, in the FTC channel or the FTC detector, 95% of the light is from FTC, which is correct. But 5% of PE is getting collected in the FTC channel, which I need to remove. Okay. Similarly, in PE channel, 87% of light is from the PE fluorochrome, but 13% of light is from FTC fluorochrome, which I need to remove. This is wrong. So I will be doing a mathematical calculation, which is software driven. You don't you don't do it manually. It is a software driven automatic calculation. And what the software does is, it will remove this non-specific signal from the other fluorochrome, and it will give you the correct thing. This is called compensation. So similarly as this, so red is removed from the green and green is removed from the red channel. Okay, so this is called compensation. Clear? So this is called spillover table, where, as we saw, so FTC, 100% of FTC light is there in FTC, but a part of PE is coming into FTC. Similarly, if you find PE channel, 100% of PE is in PE, but 22% of FTC light is getting into PE channel. Okay, and similarly, third per CP, you find 1% of FTC is coming into the per CP channel, and 0.6% of PE is coming to the per CP channel. Okay, so we need to remove all these. The one which are circled are all spills into other channels. So we need to remove that. So if you see, FTC is spilling over into PE 22%, and it is spilling over to 1% in per CP channel. Okay, similarly PE 0.5% is spilling into FTC channel, and 0.6% it is spilling into the third channel. Similarly, per CP, the third fluorochrome, it is not showing any spillover in PE or FTC. It is getting detected only in the channel or detector which is dedicated for it. Okay, so this is very important. So this is called spillover matrix, and when you put an inverse of spillover matrix, it's called compensation matrix. The actual compensation matrix I'll show you in the subsequent slides. Okay. So is there a way to avoid compensation totally? So there is something. Is there? Okay, fine. Autofluorescence is different. Autofluorescence, I'll tell you what is autofluorescence and how to check with autofluorescence, I'll tell you. Now, is there a way to avoid compensation totally? Anyone? So before I go into that, is now spillover clear? You know what is spectral overlap, what is spillover, and is that clear? And the process of removing the spillover is called compensation. Okay. Now, I suppose it's clear till now. So I'll go ahead. So is there a way to avoid compensation totally? Any answers? You feel? Okay. Is there any way? No. There is a way. There is a way to avoid compensation. Any answers? Anyone? See, for example, I'll tell you why compensation has to be done, because spillover is happening. Now, if I use fluorochromes which does not have spectral overlap, then spillover will not happen. Then I need not do compensation. See, this is an example what I want to show you. Now, this is a select fluorochromes which does not show overlap in emission spectra, or select fluorochromes which does not show spectral overlap. Okay, now you see this is a blue laser 5-color instrument. Okay, because I'm saying 5-color because it has 5 detectors. Okay, bandpass filter, so it means 5 detectors are there. If I use 2 fluorochromes, for example FCM and one more fluorochrome like PC7 or PC5, where the emission spectrum of these 2 fluorochromes are not at all overlapping, then there's no need for compensation because there is no overlap at all. In contrast, if I'm using 2 fluorochromes which are like FCM and PE, where there is a spectral overlap, I need to do compensation. It is inevitable. I need to do compensation. But if I'm doing a simple 2-color instrument, 2-color experiment where I need just 2 fluorochromes, and I select the fluorochromes in such a way that there is no spectral overlap in between them, then spillover does not happen, and there is no need to do compensation. So that is one. So if you want to avoid compensation, you need to select fluorochromes where there will not be any spectral overlap. And the other way of also avoiding compensation is you need to select fluorochromes across lasers. For example, you take 1 fluorochrome or 2 fluorochromes which are excited by violet laser and they don't have any spectral overlap between them. Similarly, you take 2 fluorochromes from 2 fluorochromes which are excited by blue laser and which don't have any spectral overlap. And similarly for red laser, you take fluorochromes which does not show any spectral overlap between them. Now, if I do like this, so this is a 3-color instrument. So conventionally speaking, it can detect up to 10 colors. But fearing of compensation and spillover, I can able to use only 4 fluorochromes. Or I can do only 4-color experiments in a 3-laser instrument which has a capacity to do 10-color experiment. Okay, so I'm because of avoiding compensation and spillover, I am 6 particular fluorochromes I'm not using. So that's a compromise. Correct? So you can avoid compensation like this, but if you want to use the machine to its maximum capacity and utility, okay, compensation is inevitable. Okay, because the same 3-laser instrument, I can use it for 10 colors. I can beautifully do leukemia, lymphoma. Okay, but if I need to avoid compensation and spillover, I can do only a 4-color experiment. Okay, so compensation is, especially when you're doing multicolor flow cytometry, compensation is inevitable. Compensation is inevitable. Okay, so you need to know that. And this compensation spillover will happen maximum with tandem dyes or between 2 adjacent fluorochromes with respect to their emission range. Okay, I'll show you that in the subsequent slides. Okay, now spectral spillover occurs most significantly from a fluorochrome into an adjacent detector. For example, FCM is 1 fluorochrome. Okay, the adjacent detector to FCM detector is PE detector. Okay, so some amount of FCM light will get spill over into the PE detector. Okay, so that is what the point is. Spectral spillover occurs most significantly from a fluorochrome into the adjacent detector. So if I have FCM detector and PE detector, the fluorescence light of FCM maximum will be captured by the FCM detector, but a part of it can be collected in the PE detector because the bandpass filter of PE detector, the sunlight of fluorescent FCM light will go through the bandpass filter of PE detector and it will be collected in the PE detector and signal you will get it in PE channel. Okay. For example, light from FCM fluorochrome will also be detected by FL2. So this is a spillover signal, okay, which is used only to detect P. Okay, so this is what. Okay, and spillover also occurs between laser lights. For example, as I said, normally spillover maximum occurs between the fluorochromes which are excited by a same laser. For example, if I'm using a red laser, spillover will commonly occur between APC 700 and APC 750. All these three fluorochromes are excited by red laser. So spillover between these three fluorochromes would be maximum. But sometimes spillover of these fluorochromes can happen in other channels, which are other fluorochrome channels excited by different lasers. For example, blue laser or violet laser. That can also happen. Okay. So if you find here, see FCC signal. This is FCC positive population, which is spilling over into PE. Okay. If I correct it, it will come this way. If I correct it, it should come this way. I'll show you in the subsequent slides. Okay. So you need to know. So the point here is spectral spillover commonly occurs between fluorochrome occurs significantly from a fluorochrome into an adjacent detector. If you find FCC detector, the adjacent detector to FCC is PE detector. So fluorescence from FCC can spill over into PE commonly. Similarly, spillover would be maximum among tandem dyes, tandem and parent dyes. Because for example, APC 700 and 750, the spillover between these three will be more when compared to other fluorochromes. Okay. So this is a beautiful diagram which is showing you how the spillover is happening between the fluorochromes. Now FL1 is FCC channel, FL2 is PE channel, FL3 is ECD, FL4 is PC5.5, FL5 is PC7, and these are the respective fluorochromes here. Okay. Now if you find FCC, okay, so FCC should be collected ideally only by FL1 channel. But if you find here, some amount of FCC is getting collected in FL2 channel, which is the PE channel, and a very minimal amount is also getting collected in ECD channel. Okay. Similarly, if you take PE fluorochrome, okay, it is getting collected in PE channel, which is ideal. There is no spillover into FCC channel. Okay, so you will not get PE signal in FCC, but you are getting signal in its tandem. The tandem of PE is ECD. You are getting a spillover of PE into ECD, which is FL3 channel, and you are getting a spillover of PE into FL4, which is PC5.5. And similarly, you are getting a spillover of PE into PC7. So these two are tandems of PE. Okay, so you are getting spillover like that. Similarly, if you take the third one, ECD, you see the maximum spillover is happening with PC5.5, which will be collected by the FL4, fourth channel. Okay, FL4, and a part is also spilled over into FL5 channel. Similarly, you find any fluorochrome, it's getting spilled over into its adjacent detectors. That's the point here. So mostly it gets spilled over into its adjacent. Adjacent means either nearby detectors. If you find the adjacent detector for FL7 will be mostly FL6 and FL8. So FL7 signal, which is APC 700 light, emitted fluorescence can be detected in APC channel as well as APC 750 channel. That's how you need to see. Clear? So we need to, this is before compensation. Once you compensate, these all should go off. You should get only this. So ideally, the emitted fluorescence of that particular fluorochrome should be collected only by the detector or channel dedicated for it. No other signal should come into it. Okay. So how will you compensate? So as I said if you want to compensate, run a sample stained only with FCC. Okay, FCC labeled antibody. Observe the FCC signal in all other channels. Okay, theoretically, there should not be any signal of FCC in other channels except FCC channel. Okay, so if you get a signal in other channels, then you need to compensate it. Make it negative. Okay, adjust the compensation setting until no FCC signal is seen in the other channels. Okay. Do the same for all other fluorochromes. So once you finished FCC, you need, if you are using a 10-color instrument, okay, so the channels what you have is FCC, PE, ECD, PC5.5, PC7, APC, APC 700, 750, PB, KO or NER. So you need to do for all the 10 fluorochromes. Here it's FCC, right? So after finishing FCC and once you see there is no FCC signal in other channels except FCC, then you do PE. You take the cells, stain it with PE, run it. You should get signal only in PE. If you're getting signal in other channels, you need to compensate, make it 0 and make sure only you're getting in PE and then go for the third fluorochrome. So you need to do for all the channels which your machine has. Okay, if it's a 10 color, you need to do it for 10 fluorochromes. If it's a 5 color instrument, you need to do for 5 fluorochromes. If it's a 13 color, you need to do it for 13 fluorochromes you are using. So this is how you do compensation. Okay, so how do you do this is we have controls for compensation. Okay, before I go into that, any doubts? Is that crystal clear? If you have any doubts, please put in chat box or you type your name. I'll unmute you so that you can directly ask your question if you feel sick of typing. If everything is clear? Any doubts? So, shall I go ahead? Is someone typing? Fine then. So I'll go ahead. Right. So how do we do this? You use something called compensation controls. So what we saw is just now is single stain control, where we take the sample, stain it with one particular fluorochrome and see for signal in other channels whether it is spilling over. Okay, that is called single stain controls. And the other type of controls is unstained control, where you don't use the fluorescence, the antibody itself. You don't use any fluorochrome. You just run the cells without staining them. Okay, I said what is staining in flow cytometry. Staining is adding fluorochrome tagged antibodies to the cells is called staining, right? Unstained controls are cells. Just take the cells, okay, and run it in the machine and check whether any non-specific signal or what we call it as autofluorescence is coming. Non-specific or false positive signals. That is called, so unstained controls we do to check autofluorescence or non-specific signals. Okay. Then there is something called fluorescence -1, which was used earlier, now currently not widely used. Fluorescence -1 is opposite of single stain controls. In single stain controls, what we do, we stain it with one particular fluorochrome. We run it in the machine and check for that signal in all the channels, right? Whether it is spilling over and it's giving a false positive signal. Fluorescence -1 is you stain with all the fluorochromes except the fluorochrome which you want to study. If I want to see whether is there any non-specific signal in FCM, okay, from other fluorochromes. If I want to see whether any non-specific signal in FCM channel from other fluorochromes, what I do, I stain the cells with all other fluorochromes except FCM and run it. Now, if I get a signal in FCM, positive signal in FCM, that means it's a non-specific signal because I've not added FCM. Okay, so fluorescence -1 is exact opposite to single stain controls. Single stain, we stain the cells with only one particular fluorochrome and check for its signal in other fluorochromes, other channels. Okay, PE channel. If I am using only FCM stain cells, I will check for FCM signal in PE channel, ECD channel, and all the channels. Okay, fluorescence -1 is completely opposite of single stain controls. Okay, but to do this, you basically need cells or beads. Okay, beads are nothing but commercially available spherical particles which are equivalent to cells but not cells. Okay, so these are used for doing all your quality control purpose because they have reproducible fluorescence and reproducible parameters with them. Okay, so these are commercial, something like our CPC controls, internal controls. We have beads, so we can either do compensation with cells or beads. Why I want cells or beads? Because what we are discussing about this fluorescence spillover compensation is all related to fluorochromes, but we need the fluorochromes to attach with something. Correct? You can't just use the fluorochromes and in the flow cytometer. You need the fluorochromes to attach with something, which could be either cells or beads. Okay, so this is what I mean. Okay, sorry. So this is the fluorochrome and the compensation is all related to this. But we need cells where this particular antibody will go and bind. Okay, and we also need cells or beads for that, and we also need the antibody. Okay. Right. So this is compensation controls. We'll see about single state controls. So cells or compensation beads stained with single fluorochrome. That's what I was saying. So if I see, this is a 3 fluorochrome panel. Okay, so I have an experiment where I'm using 3 fluorochromes and I want to do compensation for this particular 3 fluorochromes, which is FCM, PE and PI. Now what I need to do is I need to use a single tube only for FCM, a single tube only for PE and a single tube for PI. So that means in FCM only I'll add only FCM fluorochrome. Okay, I'll add only FCM fluorochrome. In PE I will add only PE fluorochrome. In PI I'll add only PA fluorochrome, and I'll also have unstained where I have not added any fluorochrome. Okay, now I run every tube in the machine. While running this tube, after running this tube, I'll check for any FCM signal in PE channel or PI channel. Okay, ideally speaking, there should not be any FCM signal in PE or PI channel. If it is there, we need to correct it. Okay, similarly, after finishing FCM, I will run the PE tube in the machine. The PE signal should be ideally be there in the PE channel. If there is any PE signal in the FCM channel, then we need to correct it. Similarly, if there is any PE signal in PA channel, that has to be corrected. Similarly, third, I need to run the PA stained tube where the signal should be available only in the PI channel, but if it's there in FCM or PE, it has to be corrected. So this is how we do single stain controls and then compensate. Okay, so we use one tube for one particular fluorochrome, run it, see for signal in other channels. Second, run it and check for fluorescence in other channels. And similarly, we need to do for every fluorochrome which is being used in your machine. Okay, so what are the requirements for a single state control? So if you are using a single state control, it should contain a clear, well-defined negative and positive population. What I mean to say is that, see, this is a well-defined negative and positive population. For example, if I'm going to do compensation for a 10-color panel, okay, what the antibodies or cells, I told you, right, you cannot compensate only with fluorochromes. You need either cells or beads and also an antibody to which the fluorochrome will be attached. So you need cells or beads and corresponding markers to do compensation for the fluorochromes. So when you're selecting such antibodies, you need to select markers where you get bimodal population. I'll tell you an example. Can you use CD45 to do compensation? See, if you use CD45, all the cells in the peripheral blood will be CD45 positive because it's a common leukocyte marker. Okay, and you will not have any negative population at all. So it's not good to use CD45 as a compensation control material. Okay, instead you can use CD19, CD3, CD4, CD8 because if these markers will show you a positive signal as well as a negative signal. So you can use these markers for doing a compensation. Okay, so requirement is there should be a clear, well-defined negative and positive population. The positive population must be as bright or brighter than the brightest experimental sample. Okay, so if you are doing an experiment with, say for example, you encounter some bright cells for, say for example, I'll tell you mass cells. Mass cells are bright for CD117. So when you are using 117, okay, you should use such a population. You should not compensate with a dimmer population because when that bright comes, it can again have spillover problems. Okay, so must use the exact fluorochromes used in your experimental samples. For example, you are using FCM in your experiment. You cannot compensate with other fluorochromes, similar fluorochromes. For example, Alexafluor 488, which has the same excitation emission almost like FCM. But you are using FCM in your experiment, you cannot use Alexafluor 488 for doing compensation. You should use the same exact fluorochromes. Okay, so ideally will be aliquoted from a same tube of fluorochrome as was used in the experimental sample. So you will be using the same fluorochrome which is used in the experiment. Okay, now there is something called let's see about beads and then cells. Okay, which is used as compensation controls. So there's something called beads. Okay, now what are these beads? So these are all, as I said, spherical particles, and it consists of two populations of such populations, microparticles, which can bind to kappa light chain. So these particular beads can bind to kappa light chain because it is manufactured in such a way that these beads have kappa light chain areas. So when you add any antibody, see whatever markers what we are speaking about is all antibodies, right? So these antibodies have a kappa. So this will go and bind to the beads. So any antibody, whatever antibodies you have in your lab, any marker you have in the lab, if you add, that antibody will go and bind to the cells. Okay. In contrast to cells, because cells will bind only to that specific antibody. If I'm using T cells, if I use lymphocytes, it will bind only to lymphocyte markers. It will not bind to granulocyte markers. Correct? But if I use beads, since the binding site in this bead is a kappa light chain, kappa light chain, every antibody has a kappa in it. So it will come and bind to that particular beads. Okay. So provides two population of microparticles which bind any kappa light chain bearing immunoglobulin. That is antibodies. Okay. And the negative control particles have no binding capacity. So the negative beads will not have anything, will have nothing on the surface, whereas the positive beads will have anti-kappa molecules which will bind to kappa light chains of the antibodies what you are using. So when you drop an antibody to these beads, the antibodies will go and bind to the beads having this anti-kappa molecule, and the antibodies will not bind to beads which does not have anything on its surface. Okay, so you find a mixture of stained beads and unstained beads. So that is the advantage of using these beads. So in one particular beads itself, you will have unstained population and stained population. So when mixed with the fluorochrome conjugated antibody, the COM beads provide distinct positive and negative stained populations that can be used to set compensation levels manually or automatically using machine setup. Okay, this is about beads. Okay, for example, now how this is done. So this is a FITC stain control. If you find this is a FITC negative population, okay, so this particular population before compensation it will be here. Okay, so once you do compensation, you will be, after running the controls, you will give an automatic compensation and this population will be dragged down to this particular area. So this is after compensation. Okay, so similarly you find this. So this is the plot, this is the FITC channel, but I have run only FITC. Okay, now you find a non-specific signal in the PE channel. Okay, so once I do compensation, what automatic compensation, this population will be dragged down because I know that this is non-specific because I've used only FITC stained population. I've stained the cells only with FITC. So this is not possible. Okay. So once I run this and if I find something like a spillover into the PE channel, I'll automatically compensate with the machine software. So what the machine does is it will pull down the population here. Okay. And finally it will come like this. Okay. And you need to check the median of these two populations. I'll tell you for to check whether the compensation has been done correctly. These are statistics. I'll show you how it's done. Okay, so what do you want to use? I said to you that there are two options available to you. You can either use beads or cells to do compensation. Beads, I told you about comp beads. Those are called compensation beads. Or sometimes you can also use cells. What are the advantages and disadvantages of both? Beads, it is very easy to use because it's ready to, if you buy that commercially, you can use it. Can use with any antigen because it has anti-kappa molecules on it. So you drop any antibody which is there in your lab, it will go and bind to it. Okay. Not a perfect match because you are working with cells. You are working with cells or samples. Okay. So beads are not exact matches. Cells are more similar to the material what you work with. We normally work with cells, right, in clinical flow cytometry. So cells are a better match, but beads, you can use it for compensation, but it is not the exact match as your biological samples. Better separation between negative and positive population. We saw that, right? Because you have a mixture of two beads. One is one which does not get stained because it doesn't have any molecules on its surface, whereas the other population has, which will bind effectively to the antibodies what you drop. Any antibody will go and bind to it. So you have a better separation with negative and positive population. Okay. The advantage is cells are a better match to fluorochromes in the panel because that is what you're working with in your regular flow cytometry. Okay, it takes more time to stain the cells because If you take peripheral blood, you have to lyse the RBC, then you have to stain it. So these are all some of the difficulties. And specimen for each type of antigen could be difficult. So here the advantage is you drop any antibody, it will go and bind to the beads. But here cells, as I told you, if you are taking peripheral blood and you want to do compensation with the lymphocyte population, you cannot use a granulocyte marker, which is not there. Similarly, you cannot use other markers which is not present in that, erythroid markers or something. So that is a problem. So you need to select that specific population to compensate. Okay, works well if the antibody used is bimodal and rightly expressed. So as I said you right, CD45 you cannot use because there is no negative control in peripheral blood. So but if you use CD3, CD19, CD4, CD8, those populations have negative. For example, if you use CD19, T cells will be a negative control and B cells will be a positive control. So you get a negative population as well as a positive population. So you need to select such cells. Okay. So final cells. So to be if you see in the regular practice, cells are more representative. Use peripheral blood sample with 20% lymphocyte because the lymphocyte is a population which you will be using to come as compensation controls. Lymphocytes are best since no autofluorescence. You know what? There is no granules in the lymphocytes, so there is no autofluorescence. Okay, so it is used. And one more advantage with lymphocyte, it shows bimodal population. If you are using CD19, again you get negative with T, positive with B. If you are using CD4, helper cells will be positive, all other cells will be negative. If you are using A, cytotoxic will be positive, all other cells will be negative. CD3, T cells will be positive, B cells will be negative. So that advantages you have with the lymphocytes. And similarly, it has all the three, negative, dim and bright. Monocytes are dim positive for CD4. So lymphocytes are the best controls. You should know what markers are expressed in normal cells as well as okay. So you should know what are the cells which express what markers. For example, CD3 and 19 are not co-expressed. So if you find something co-expressed between CD3 and 19, that means there is something wrong. There is a spillover. So these things you should know. Okay, cell should express the marker bright. It should, as I said you, when you are doing compensation, the marker should be bright enough. There is no use of using a marker which is dim for that particular fluorogroup. Then when you get during in your regular samples or experimental samples, to get a bright signal for that particular fluorogroup, then there may be a spillover in other channels. So that also has to be done. Okay. So this is how we do compensation. This is normally done by the application specialist. He comes and does the job for you. But you should know what is happening, and if there is a need, you can also do it. Okay. Now, I'm not using beads here. Okay, beads are available. Beads are very simple. You get compensation beads. You drop any antibody, it will go and bind. Okay, all you need to do is that you need an antibody of that particular fluorochrome, which is there in your panel or experiment. Okay. So here, what I'm doing is I'm allocating one particular tube for every fluorochrome which is there in my experiment. Okay. Starting from FITC, PE, ECD, 5.5 PC, 7 APC. Okay. And then I'm selecting antibodies, okay, which are lymphocyte markers. For example, if you see here, CD4, CD5, CD8, 79B, 19, see all are lymphocyte specific markers so that I get a negative control as well as a positive control. Okay, so selecting the antibodies or markers is also an important thing. So I have selected cells as my controls and I have also selected the markers now. Okay, so what I need to do in FITC, what I will do, first tube, what I will do is, it's a FITC control, right? So I'll add only FITC fluorochrome into this. Okay, then I will acquire this particular tube in the machine. I'll see whether signal is coming in other channels except PE, except FITC. Okay, so if there is signal in any of the channel other than FITC, it means it's spilling over. Then I need to do auto compensations to correct it. Then I need to run the PE tube. Again, I need to check all the channels whether signal is coming. Ideally, only PE channel, there should be a positive signal. All other channels should not show a positive signal. If there is a positive signal in other channels other than PE, then you need to compensate. So you need to run one of the one by one, compensate, and finally, once you finish all the 10 fluorochromes, you have done adequate compensation. Okay, this is how compensation is done with controls. Okay, so before compensating, adjust the voltage so that the negative population is kept right. So that is why the reason I told you, you should have a bimodal population. When you are compensating, your control should have both negative population as well as positive population. So for example, if the negative population is lying here and the positive population is somewhere out, you need to adjust the voltage of the detector so that this negative population come to this particular area. Okay, so that the separation between the negative and the positive will be good. Okay, so bringing this population from here to here, okay, is done by adjusting the voltage. Okay, so the negative population should be kept in the negative area. Okay, and then you need to start doing compensation. Very important take home message: don't adjust voltage after doing compensation. You should not touch the voltage of fluorescent detectors after doing compensation. Before compensation, you can adjust the fluorescent detector voltages just to bring your negative population here. But once you have done compensation, you should not touch the voltage of fluorescent detectors. What I mean to say is, you can touch forward scatter, side scatter, but fluorescent detectors, you should channel detectors, you should not. Voltage of fluorescent detectors should not be touched. Okay. Now I told you what is fluorescence -1. This is not currently used. It is used previously. Before I go into that, any doubts? Any doubts? Should I unmute anyone, or you have any doubts? You can unmute yourself. You can just unmute yourself and you can ask your question. Practically, you feel anything not clear? You can type your question in the chat box also. Is it clear? Yes. So if beads bind to any fluorochrome labeled antibody, then how to differentiate negative and positive population? See, I told you now, beads is a mixture of two. The beads, the comp beads will be a mixture of two beads. One will not have anything on its surface, so it will act as a negative one. Okay, one will have anti-kappa molecule. So if you add antibodies, it will go and bind to it. So when you run the beads together, then you will get two populations. Correct? Dr. Anand, you are getting me? So, how to differentiate between positive and negative? See, for example, I'm telling you from the beginning. So there is a comp bead bottle commercially available. Okay. So this beads has two populations. One is negative. One bead will have nothing on its surface. The other beads have anti-kappa molecules on its surface. When I'm adding any antibodies, see, whatever any antibody, any fluorochrome tagged antibody will have kappa to it, correct? Because all antibodies are nothing but immunoglobulins. So when you add antibodies, these antibodies will go and stick to beads which has anti-kappa molecules on its surface, whereas the other bead which does not have anything, it will not bind to that beads. So when you run this mixture of beads in the flow cytometer, you get a negative population as well as a positive population. Okay, and remember, you are using only one fluorochrome in that bead. So I will drop FCM alone in that. I will not add any other fluorochrome because this is only single stain controls. So I need to take 10 tubes. If I'm using a 10 color flow cytometer, I will take 10 tubes, separate test tubes, add add beads into the first tube, all the 10 tubes. Then I add FCM in the first tube, P in the second tube, ECD in the third tube. ECD in the sense antibody tag to ECD. Okay, fourth antibody tag to PC 5.5 in the fourth. Similarly, I add all the antibodies tagged to that respective fluorochromes to the 10 tubes, and then I acquire one by one all the tubes and see whether any non-specific signal is coming in the other channels. Okay, is that clear, Dr. Anand? Yeah, your side is fine. How to adjust voltage? See, voltage is adjusted. You have something called there is a small outlet when you are acquiring in the machine. There is something called detector channels. When you click it, I'll be showing this during our processing class and acquisition class. Okay, so there is a detector tab will be there. If you open it, there will be voltage nearby. You have a small cursor nearby to increase and decrease it. So in that way, you can increase or decrease the voltage. Okay, voltage should be adjusted before starting to record your events. Okay, and voltage should be adjusted, I repeat, before doing compensation. Once you have done compensation, if you are adjusting the voltage of fluorescent channels, then that compensation becomes invalid. Again, you need to recompensate. Correct? Because if you adjust the voltage of fluorescent channels, what happens? We spoke about PMD, right? PMD is a very sensitive one. If you adjust the voltage, then whatever compensation you have done, again will go wasted because it becomes AY. Okay? So, is that clear, Dr. Lakshmi? And any other doubts? Any other doubts? Yeah, great. So this is very important topic. So I want you to be clear with everything. So you know what is spectral overlap, you know what is spillover now, and how this spillover is compensated, you know now, by using controls. There is called single stain controls, where you use only one particular fluorochrome in one tube and check, you run it in the flow cytometer and see for its signal in other channels. If it is coming, you need to remove them. Okay, this removal is done automatically by the software, because it's a mathematical calculation and manually it cannot be done. So that's how. So for you need to run different tubes for every fluorochrome what you are using, and finally you eliminate all the spillovers. Then you get a perfect compensation, and that particular table with finally what you get is called compensation matrix. I'll show you that. Okay, then I'll go ahead now. Right. So I said you what is fluorescence -1. This was previously used. So it is very opposite to single stain controls, where we used only one fluorochrome in one tube and we acquire and see for signal other channels. Okay, apart from the one which is dedicated for that. Fluorescence -1 is complete opposite, where you add all the fluorochromes except the one which you are studying. If I am studying what is the other signals which are coming into FITC, non-specific signals coming into the FITC channel, I'll be adding all the fluorochromes except FITC, and then I run. So I'll get positive signals in all the fluorochromes except FITC, ideally. But if I'm getting a positive signal in FITC also, that means it's basically a spillover from other channel, and I need to eliminate them. Okay, so fluorescence -1 is previously used. Now nobody is using it. FMO control contains all the markers in the experiment except the one of interest. For an FMO control, use the fluorescent markers except one FMO for each fluor in experiment. Useful to accurately define cutoff point between positive and negative. Okay, so that is basically to draw your quadrant. So if you are running, after compensating, if you are running fluorescence -1, you know where to put a cutoff between your negative population and positive population. Okay, so see, now this is an experiment. This is unstained. Okay, and this is PE FMO control. Okay, you find here this is FITC channel on the x-axis, and y-axis you have P. Unstained is beautiful. It's lying in the double negative area. And if you find if running a FMO control, that is, I've stained with all the fluorochromes except say for example FITC. Okay, sorry. Except FITC, I've stained everything. Now, if you find here, there is a non-specific signal coming in the PE channel. Okay, so if I draw a quadrant with unstained control, my quadrant will be lying here, and anything beyond this will be positive. Okay, but if you see without with FMO of PE, you find that there is some non-specific signal coming into the PE channel. So now I need to reshift my negative quadrant, this quadrant limit to this particular area. So anything above this blue line is positive. Okay, so that is what the use of FMO. FMO is just to set your negative quadrant to determine beyond which it is positive and below which it is negative. So if I just set a boundary with unstained, see, I will draw a boundary like this for PE. But if I use FMO, I can see that there is some non-specific binding signal, non-specific signal coming from other fluorochromes here. So I have raised this particular threshold to this particular area. So now I'm sure whatever comes above this blue line is only positive, not this red line. Okay, so that is the use of fluorescence -1. Okay, negative controls, I said the beads or cells, anything, you don't stain them at all. You just run it in the flow cytometer just to check for autofluorescence. If you are dealing with the case of APML, then you need to do this particular unstained tube, because APML cells have a lot of granules in them, which can show you non-specific signal as non-specific signal. So what you need to do before staining the APML cells, you just run the APML cells without staining them. You can see how much autofluorescence is coming in every channel. After that, you run the stain sample. So the unstained tube will help you to set up the negative quadrants, and beyond that, after running the stain sample, you know what is positive and negative. Okay. So this is something which we just discussed, like how to confirm that you are correctly compensated. Okay. So that is by statistics. Okay. So compensation is correctly set when the median of the negative population is equal to the median of the positive population in the spillover channel. Okay. For example, I'll tell you. So now this is a fit C. Okay, fit C is spilling over into P. Fit C signal is spilling over into P. Now I am starting to I've run the controls and then I have compensated them. Okay, I've run a fit C only control and now I have compensated them. So how do I know that it has been ideally compensated? Because I need to have a mathematical calculation to check it. So statistics. So the idea is the median of the fit C negative population and the median of fit C positive population should be same for P. Okay, that's a statistics. So during analysis, I'll show you how the statistics are. There's a software for the statistics. I'll show you that. For example, if you're using a positive fit C stain sample to apply compensation to P channel, the median of the negative and fit C positive population should be equal in the P channel. So that's what I say. So this is fit C negative population. This is fit C positive population. The PE median of this negative population and the PE median of the positive population should be the same. So now you see both. Now you see this population. It is the negative is lying here, positive is lying here. But once it is adequately compensated, the median is falling same for both negative and positive population. So now the PE signal, there is no false positive PE signal come in the PE channel. Okay, so that's how you will know you have correctly compensated. So the answer is the median of the negative fit C population and median of the fit C positive population should be equal in PE channel. Okay, so you should check the median in the spillover channel, not in the channel what you stain for. See, this is again, I'm just showing you some before and after compensation. Okay, now you see blue color is without compensation and green is one with adequate compensation. You see blue, see without compensation it is like this. Okay, for fit C. Whereas in PE you find there is a spillover. Once I compensate, see this has vanished. Okay, similarly in the PA channel you find there is a spillover because I've stained the cells only with fit C. They should not be this, even this, correct? So once I compensate it, the false positive population disappeared after adequate compensation. Okay, similarly in dot plot, this is a histogram. Okay, when you have numbers on the y-axis, it's called histogram. When you have two fluorescent markers on x and y-axis, it's called dot plots. Okay, this all I'll cover in data analysis. So here you find this is a pre-compensation population. Before compensation, it was lying here. Once you adequately compensate, it has come beautifully here. Similarly, in the other channel also, you find the blue population before compensation, and once it is compensated, it is correctly falling. Okay. So, what are the clues to know? You can ask me, sir, how can I know whether compensation is correctly done or not when I am running a patient sample, when I am doing an analysis? Okay, I'll tell you certain clues. An uncompensated population will be like an arrow pointing towards something. You see this? You see this? As if it is pointing towards something. See here? So these are all uncompensated data. You find here this one. Okay, you find here this population going that way. A point, like it is going like like a pointed arrow. Okay, here it is overcompensated. It's like this is all there. Okay, so these are some of the ideas or clues to check your population is not compensated well. So, see, this is compensation. This is correct compensation. And similarly, when you're compensating, there is a chance you can do an undercompensation and overcompensation. So you need to be doing it correctly. You find this is correct compensation. If you undercompensate it, that means you have not brought this population still down. This is a fit C stained, single stained, fit C only stained sample. Okay, you find some spillover into the PE, which has been, this one is adequately compensated, where the median of PE median of this population and this population is the same. Whereas if you find this, the PE population is still not yet brought down. If you check the median of PE for this population, it will be more than this. But ideally, if it is correctly compensated, it should be the same, right? So this is not correctly compensated. So it is undercompensated. Undercompensated, which means you need to compensate more. And over enthusiastically, if you compensate, that leads to overcompensate, where the population has gone below now. Okay, so you need to know all these things. So adequate compensation has to be done for correct data. Okay, so again, some more examples for this is overcompensation, this is adequate compensation, and this is undercompensation. Okay, so once you do a perfect compensation with single stain controls, okay, for all the parameters, all the fluorochromes you are using, you will get a box like this, which is called compensation matrix, which is an inversion of spill matrix, which we saw in the third slide. Okay, so this is compensation matrix. So once it is done, you need to take a photograph of this, so that this is the adjustment what you have done. So you need to check whenever something goes wrong during your analysis and you feel compensation has not been rightly done or compensation has been adjusted, you can open the compensation matrix and check whether it is the same settings or the same values which you captured when compensation was done. So you can do that. Okay. So sometimes what happens, the compensation would have been done, samples would have been analyzed. By that time, what happens, those compensation would have been affected, and still during analysis you can find some clues for uncompensated data. Say, as I showed you here, right? So during your analysis, during your data analysis, you can find clues for uncompensated data. Like when you're getting like this during analysis, then you need to manually or you compensate post-acquisition. That is, post-acquisition is during your analysis, if you are compensating, it is called post-acquisition compensation. Okay, so compensation is a mathematical calculation, therefore more accurately done automatically by the software than with manual calculation or manual correction. Okay, post-acquisition is manual correction. During analysis, if you are adjusting the compensation, that means it is manual correction, and it is called post-acquisition compensation. Okay, manual compensation is a process of manually adjusting the compensation values by eye. So you are seeing and adjusting it. You are not also to adjust the population. So this is called post-acquisition compensation. Okay. So to make it very simple for you, adjusting the compensation when you are analyzing the data is called post-acquisition compensation, and you are doing it by visual interpretation. Okay. So this is how we do this. See, now this is an uncompensated data, and during analysis, I'll be adjusting the compensation values like this so that it gets correctly compensated. Okay, see, this is an uncompensated. During my analysis, if I find a data like this, it's uncompensated. Now I adjust my compensation so that it gets adequately compensated. This is called post-acquisition compensation. Okay, ideally, what you need to do, you need to compensate the machine with compensation controls. But sometimes, what happens, during an analysis, you find an uncompensated data due to some reason. You need to compensate it manually like this. This is called post-acquisition compensation. Okay, so the best way to check whether your data is adequately compensated and it's perfect is check for combinations. So you check FitC with PE, FitC with ECD, FitC with PC 5.5. You check PE with FitC, PE with ECD, PE with PC 5.5. So in multiple combinations, if you check, if there is a spillover or if the data is uncompensated, you will get that arrow mark. And then you need to compensate it correctly. Okay, so that is how you can check. See, this is N by N. We call this as N by N plot. So you have so many markers and you seeing it multiple combinations. See, I can tell you now which is all poorly compensated. This is poorly compensated. Agreed? So you can find the spiking there. Okay, and what else? See, this is also poorly compensated. Okay, so these all what you need to do, you need to manually adjust the compensation so that you correct the compensation here. Here, this one is poor, this is fine, this is poorly compensated, so you need to adjust it. You can find that spiking here, it's poorly compensated. So this is how you do post-acquisition compensation. And to check whether your data is adequately compensated, check for all the combination of plots, N into N plots. That is, if you are using a 10 color flow cytometer, you use FitC with all other 9 markers, all other 9 fluorochromes. Combination of FitC with all other 9 fluorochromes. Similarly, for every fluorochrome, combination with other 9 fluorochromes. then you can know where is the compensation, how it is done, how well it is done. To set the appropriate voltage in all detectors with negative population, normally kept in the first log. I showed you, right? You need to, the unstable, the negative population should be kept in the first log, in the negative area, before doing automated or manual compensation. Never do or never adjust voltage once you have done the compensation. It is very bad. Okay, after doing compensation, you should not adjust the voltage. That is the tip. Especially the fluorescent. What I mean to say is fluorescent channel voltages or fluorescent detector voltages. Okay, during post-acquisition compensation, when you adjust only the compensation, matrix value change but not the voltage. So post-acquisition, when you are adjusting the compensation, only the compensation matrix value changes but not the voltage, because you already acquired the sample. You already acquired the sample in the flow cytometer. So the job is done. Now when you can play with the data, no problem. Okay, so when to do compensation in this question? After an instrument setup, definitely the engineer, the application specialist will do it on a periodic basis. Is better. You can draw your own limits. You say like 3 months once, monthly once, 6 months once, year. So the yearly once is too long. So you can. Some people do it on a monthly basis. Some people do 3 months once. So you can fix your own periodic basis. After an instrument breakdown and recovery, you need to do a compensation again. Any change in the fluorochrome in the panel, very important. As I said, FIT-C is there in your panel and you have compensated the machine for FIT-C, and suddenly you are using another fluorochrome in place of FIT-C, for example, Alexa Fluor 488. Then you need to compensate it for Alexa Fluor 488. Though it has same emission, excitation and emission, it doesn't mean like you have already done for FIT-C, so you can use Alexa Fluor 488. No, you can't do that. Okay, you need to compensate with Alexa Fluor 488. You need to stain only with Alexa Fluor 488 and check whether Alexa Fluor 488 is spilling into other channels. When standardizing a new multicolor assay with the tandem type, that also you need to take into consideration. Okay. See, this is what I told you. So FIT-C, it is adequately compensated. So instead of FIT-C, if I use other fluorochrome, Alexa Fluor 488, you see there is a spillover. So you need to, this is Alexa Fluor 488. Okay, I'm sorry. Some mistake. Okay, so that you need to check. Okay, similarly, single stain control, you see. So you need to use specific controls. So you should, if you are using CD3, you should use only CD3. You cannot use with other fluorochromes. Okay, so this is post-acquisition compensation. I told you. Okay, you need to adjust the voltage. So you should need to adjust the compensation matrix so that this population is brought down. Okay, like this. Similarly here, like this. So this is post-acquisition compensation. Okay. So final note is like you titrate the antibodies that I'll discuss in the next class. I discussed this during stain index, right, in the third class. So titrate antibodies before you compensate. If you use company recommended volume and compensate with that signal, and later if you reduce it, it may show false negative. So titration is very important. Every small aspect has to be perfectly followed for a desired data or a good data. Use same titrated volume of antibody for compensation and assay. Okay, so while using a compensation, when you're preparing single stain controls, you're dropping 10 microliter of FIT-C antibody, like FIT-C fluorochrome antibody. And when during your experiment, you are adding 20 microliter. That is not right. Okay, check cell concentration when using titrated antibodies, as same volume is not recommended. Okay, you need to check cell concentration also. So these are small things. I just want to tell you that before I close the session. Okay, thank you. And if you have any doubts, we can discuss. Any doubts? You can put it in the chat. Yeah, Dr. Pallavi raised hand, so I'll just unmute her.
Sir?
Yeah, you can. Yeah, please. Yeah.
Sir, why the use of FMO has been discontinued?
Basically, if you want, you can do. What is the ultimate aim of FMO is to set your negative threshold quadrant. Okay, to say anything beyond this is positive. FMO was not very useful because your single stain controls will do the job of compensation perfectly. So FMO is not of much use because, and one more is, lot of antibodies are used, right? See, as a single stain control, you will be using only one particular fluorochrome, FIT-C. Similarly, PE. But if you use FMO, you remember you have a 10 color panel. a 10 color machine.
Yes, sir.
The first tube I need to add 9 fluorochromes except FCM. In the second I need to add all the fluorochromes except PE. Similarly, I need to use so much of antibodies. And I don't get that advantage also. When single stain controls is doing the purpose for me, why should I do? FMO is done only to set up your negative threshold quadrant. So to determine beyond this is positive. So when your FMO is done when for certain assays where the resolution is very poor, that is what I mean to resolution is when you have a very weak separation between the negative and the positive. In that area, FMO can be done, but not on a regular basis, not useful. Is that okay? Clear? Any other doubts? Dr. Pallavi, is that fine? You got it? Or should I repeat? Right, if there is no doubt, shall we conclude? Okay. If you have any doubts, you can text me also. I would love to take up your questions. If nothing, no else question, then